Alright, welcome back to my channel, and today we are actually going to talk about open sets, the set of open sets. Let me put it that way. So here, we are not going to waste so much time. What we have to know about open sets is that, say I pick 2 points A, B, and I call this set an open set. And what I'm actually saying is that from our basic knowledge, is the illustration, which means that the boundaries are not inclusive, but I have all the elements within this being what I'm talking about. Okay, yeah. So all the elements lying on this line is what I'm talking about. Okay, I exclude the points A and B, then I talk about just these points. Okay, yeah. So if I want to define what's an open set is, you can easily see that when I pick any point here, I can draw a ball. Okay, there exists at least one ball, like there's a certain radius such that there's an interval which is in the AB. Okay, so there are so many points here which I can do this kind of illustration here, and they are all going to be within AB. Okay, yes. So it means that if a set S is open, then for all x's which belong to x, there exists a certain r which is greater than 0, such that the open set x minus r, x plus r belongs to the set as well. So here, this is my r. From this point to this point is my r, and I come here, this is my r. It's like radius. Okay, so this is my r, this is my r. So when I draw the ball is always going to lie between the points A and B, and that is what makes it open. Okay, so in other sense, you can also define S to be open if for every x there exists a neighborhood of x which belongs to or which is contained in the set S. Okay, yes, so that is the definition of an open set. So examples of open sets include 1, 3, 2, 4, 3, 5. These are all open sets. Okay, yeah. And on the contrary, we can talk about closed sets as well. We can talk about closed sets, and closed sets is actually the complement of an open set. Closed sets, the complement of an open set. Okay, so if you have any open set, then its complement gives you a closed set. The complement of every open set is a closed set. So for instance, if I pick this point 1, 3, its complement is going to be starting from negative infinity to positive 1, closed, union, closed at 3, up to positive infinity. Okay, so you can actually see this as closed at 1, this one to close at 1, so it is a closed set. Even though it might be closed and open at the same time, it is closed. Okay, so the complement of every open set is a closed set. You know, you can't close your infinities. All right, yeah, very good. So set is said to be closed if its complement is an open set. If its complement is an open set. So let's talk about certain things here. Open sets contain all but only their interior points. And closed sets contain all their limit points. I have to limit point. Okay, so open sets contain all but only their interior points, but closed sets contain all its limit points. So interior points are limit points of a set. Okay, interior point is a limit point, but not all limit points are interior points. Okay, yeah, so let's use this to illustrate that. If I have the open set 1 3, okay, then 2 is an interior point, so interior point lies within. So when I go back to this set, which is open over here, whatever is in here lies within the point AB, so they are all interior points. Okay, yeah, but we want to define what interior points really are. So we could see that when you picked any point within the point AB, there is a certain R such that, okay, its neighborhood was existent in the set AB. Okay, yeah. So what we are basically talking about here is that when I pick the point 2, I can pick a certain radius, say 0.5. The neighborhood of the 0.5 neighborhood of 2 is going to be 1.5 and 2.5, and you can actually see that the 1.5 to 2.5 lies within this, so 2 is an interior point. But when I pick 1, okay, anytime I pick 1, when I pick 1 here, when I pick 1 over here, anytime I pick a neighborhood of it, I have a portion leaving the set. I have a portion leaving the set, but we are expected that the neighborhood of it should lie within, entirely within the set AB, which is not happening here. So it makes 1 not an interior point, and so does it happen for the point 3. Okay, so all the elements between 1 and 3 are interior points, but 1 and 3 are not interior points. Okay, then for closed sets, we are saying that it contains all its limit points, and here we call 1 and 3 limit points. Why? When I pick the closed sets, assuming that I have the closed set 1 3, 1 and 3 over here, when I pick 1 over here, the definition of a limit point is that when I have a limit point, then for every neighborhood of that point, for every neighborhood of that point, or the neighborhood of that point should always contain a point in the set S. Okay, so when I pick 1, every neighborhood you can think of, will contain elements which are in S. It doesn't necessarily mean that the whole thing should lie entirely in it. Okay, yeah, so that is what a limit point is. So you can easily see that all the points within these are limit points, because you have elements always being in the set S. Okay, so the only difference between the limit points and interior point is that for the interior point, it should lie entirely within the sets, which means that there's always a certain R such that the neighborhood, okay, you have x minus r, x plus r, line entirely between the sets. But for closed sets, when you're talking about the limit points is a point between, or the point in the set, such that it could even be outside the set. And what should happen for it is that for any neighborhood of that set, okay, you should have an element which lies within the set, and that is what we are talking about here. So an example of closed set is 1 3 close here, and this one is an open set. Okay, so these are basically some facts we have to know about open and closed sets. All right, so see you in the next video.